might face some network disruptions. So today we are going to get into sorting. Okay. Before sorting, I gave a small introduction about searching, right? Do you remember binary search we did? Yes. So searching and sorting are two primary activities which have a lot of applications in all the kind of operations we do with any type of data structure. So searching, linear search is one where you go incrementally search one character by character, and binary search is where you find the midpoint and then you search the left side if it's smaller, or you search the right side if it is bigger, right? So that we already discussed. And I hope all of you are aware of the recursive iteration version versus recursive iteration, which I'm not getting into detail. Now, once we complete sorting, we will have a good understanding of all the linear based data structures and its applications. So today's class, I will focus on some of the sorting techniques, and then we will go into a detailed comparison of those sorting techniques, whatever is possible in the upcoming class. And then what I'm planning to do before we move into nonlinear data structures like trees, etc., we will do some of the most common and most important applications. Okay. Some of the applications are already, like, for example, detection of a cycle in a linked list, some of prefixes, uh, and these are some of the common use cases. So if you open any kind of data structure interviews or any kind of data structures course, there are some common examples: substring of, reverse string. So these are some of the common examples you will have in any data structures question paper or etc. So we'll look at some of the complex understanding of those examples after we complete all the linear based activities. Okay, so that is my idea. And for the examination, you will have till binary trees. So we'll have two more sessions. So can we have one additional session which I missed on August 17th next week, 2 to 4? Do you have any lab sessions scheduled on that day, September 13th? Can one of you check and confirm? Yes. I'll give you the mic access.
Scheduled.
Sorry?
No sessions are scheduled.
Okay, can we
It's
do
13,
what?
ma'am.
Sorry?
Yeah, yeah, same. No schedule, ma'am. I'm saying that only.
Okay. So 2 to 4, we'll have one session. And Sunday, as usual, we'll have this session. So I can complete all syllabus for the mid-semester. Okay, because by next week, we will have mid-semester exam by third
Yes,
week, right? So this is
yes.
what I'm planning. So we arrays we did, stacks we did, list we did. So today I will cover some sorting methods. Okay, and we'll do comparison, and this has to be the trees and binary trees alone. Basics only. Okay, this all will not be there.
Okay, ma'am.
So this will be the syllabus for the examination. So I will try to complete by the additional session. Okay, I will let you know because I have a few classes also on Saturday. I will see if
Oh,
I can change them. I'll post through announcements, but mostly 2 to 4 we will have this data structures class. Okay.
okay, ma'am. Okay.
Yeah, and all the PPT are there. Please go through when you prepare for the exam. Please watch the video lectures and use the PPT as a reference. Previous year question paper also I have uploaded for your reference, so that you can prepare well. Okay, at the most try to attend the regular examination so that it is easier for you to score well. Okay. Now getting into the topic, which is on the sorting algorithms. Now we will today look at some of the sorting methods. Now, what is sorting? As simple, we know that we are going to arrange them in order, right? So let me ask you a question. Where do you think sorting will be useful? Any real-time application you can tell me? Where sorting will be useful?
Ma'am, in gallery, ma'am, we used to arrange
Yes, to sort
photos.
based on date, right? That's a very good example of
Yes.
sorting, right? Now, when you look at many real-time applications, sorting is not simple as sorting numbers. It involves a little more than what we have to sort numbers. Okay, but all the examples we sort today will be just numbers because we are using the simplest element to demonstrate sorting. But generally, in real time, date sorting is not as simple as number sorting because you have to look at the year, month, date, and then also the time if there are multiple elements on this. Right? Time also differs by region to region. So it's a little complex. Similarly, any other sorting application you take, very few sorting applications is just sorting of numbers. But there are many more places where we don't just sort based on numerical order, etc. There is lexical order. We have to sort it alphabetically, or we have to sort it based on some category, or we have to use some basic data to do that, right? So sorting application is huge, but sorting uh, requirements are not that simple. Though we will use small example numbers to teach the different sorting methods today, but sorting has been an area where we have been always trying to improvise the performance at some point of time. The reason why we are doing that is basically this sorting is a very important and a very frequently used activity. So we do not want many resources, performance time to be allocated for this activity. We want it to be as efficient as possible. So that is why we have different sorting methods. We choose best. We compare the alternatives. We don't want large amount of time to be spent on just to sort information. We want it to be quick enough, right? So the output of any sorting algorithm is it should produce the output in the order which we require, right? So the previous element should be smaller than the next element. That's the desired order, right? And the output is nothing but a combination, a different order of the input. There is no new input coming in, right? Unlike a search means you are bringing in a new input. You are taking a key value from the user and you are sorting it. Sorry, you are searching for it. So there is a new input coming in, but whereas in a sorting, there is no new input. You're just getting a command to sort from the user and you are sorting it. So the output is nothing but a reordering of all the original elements. The elements are already existing. You have all the input elements, but you're just reordering the elements. This is what is happening in the output. So the output is nothing but a non-decreasing order of the various elements which are present. Now, what exactly are the different? Why do we have? You have heard of the names in the handout, or you would have heard it elsewhere also. In C programming, also, I think you would have learned some sorting methods, right? What are the sorting methods you have learned there in C programming? In computer programming course, you learned some
Ma'am,
sorting.
Bubble sort.
Okay, you learned bubble sort. Okay. Any other sort you learned? Okay, maybe bubble sort is sufficient enough. So you'd have learned bubble sort, and you'd have heard of the other names, even if you have don't know how to use merge sort, quick sort, insertion sort. There are different sorting methods are there, right? Why do we have so many sorting methods? Or what is the reason behind why it is getting new methods are coming up? Why are we sorting it again and again? Is to improve the time and the space efficiency. And as like one size doesn't fit all, there are multiple requirements of sorting. So maybe bubble sort is best in one case, but the merge sort is best in the other case. So based on the specific requirements, we can choose the desired sorting algorithm. So we say a sorting algorithm, or we categorize a sorting algorithm based on how much extra space it requires, or does it do it internally with its existing place itself. So basically what is sorting? We have a set of numbers. Okay, say this is an array. It has some numbers. Okay, I want to reorder these numbers, that's all. So I have to put this here, maybe put this here, put this here. That's how order. So if it changes internally among itself without taking any additional space or memory, that is called as an in-place sorting algorithm. So if the algorithm does not use any extra space for manipulating the input, but requires a small constant extra space for its operation alone, then we call it as an in-place algorithm. If only the same input, but if I want to sort it in another place, there are some sorting algorithms where I will create a new array. I will take one element from here, place it here, then the second element here, I place it here. So if I do this way, it is not in place. Okay, I'm using an additional memory. So we call it an algorithm as a in place or non in place, or it uses extra memory. We don't call it in place. So based on that, we categorize an algorithm. Based on its working, it can be an in place sorting algorithm or not. A sorting algorithm is called stable if it does not change the order of elements with the same value. That is, if the position is already known, right? We don't keep changing it. So in the first place itself, you reduce. So when you have sorted one element, it's in position. Next time you iterate only on n minus 1 elements. You don't iterate on the entire n array. And next time you do only n minus 2 elements. So every time you doesn't change the order of elements with the same value. That is where we try to be stable algorithm. Okay. So we have different kinds of sort, bubble sort, selection, insertion, merge, all that. Okay, we will talk about some of them today, and the remaining we will discuss in the upcoming sessions. So I will not discuss this table now, but I'm just showing you this table so that tomorrow, when after looking at how the algorithm works, we will be able to come and validate this. Okay. Bubble sort is both in place as well as stable. Selection is in place, insertion is in place, quick can be both in place as well as other ways, but in place option is also possible. But merge sort does not have an in place option at all. It has to be copied into a new place, but it is stable. Quick sort and selection sort are not stable because you may change the altering algorithms only at the end, right? You will have the stable values. So you keep repeating for the entire array. So now, when analyzing the performance of different sorting algorithms, how do you decide which is better, right? So when always we have known that when we compare algorithms, how do we know which was better? How do we decide which algorithm is better? What is the instrument we have to measure it?
Time and space complexities.
So always we have time and space. So the same thing only we will use. How much extra space is requires and how is the time, which takes lesser time. That is how we decide which is the best algorithm. So to be more accurate, how many comparisons it does, the number of times the records in the list will be moved. You have to keep changing. The time complexity, best case, average case, worst case. Stability is when equivalent elements or records retain the relative positions even after the sorting is done. I'll talk about more about stability very soon. Okay, but what is best, worst, average case? Let's take a sequential search. Sequential search is linear search. Okay, what is the best case? You find the first item of the array to be k. Worst case, you have to go through the end of the array and then only get the value of k, or you don't get the value of k. You have to search the entire array. And average is somewhere in between itself you find the k. So these are the three cases. Similarly, for sorting also, for every sorting algorithm, you will have a best case performance, worst case performance, and an average case performance. Okay, so some sorting algorithms can in one pass of the entire array itself, if they are able to sort the entire array, then that's a best case. If you have to do n-1 times or maximum n times, etc., then it becomes the worst case. And somewhere in between is the average case. Okay, so that is what we will decide. Now, this table, you can just have a look at this table, but we will not discuss this now because we are going to look at it in detail. Okay, only thing you have to take away is we will be looking at each of this worst case complexity. By looking at the algorithm, we will learn how to compute it. Okay, and then come back to this table to do a comparison. Okay, only thing you have to remember is what is the incremental. So n, which is the best in terms of worst case here? Which is the best algorithm out of this? In terms of time alone, tell me by looking at this table. Which is the best algorithm?
Bubble sort.
Why bubble sort?
Theta and best case. Its best case is O of n in, and worst case is n square.
So don't look at best case. Always we look for time complexity, we look at worst case only, right? So tell me,
Yeah.
looking at the worst case, what is the best algorithm? N log n is greater than n squared or less than n squared? We discussed this some time back. So what is the incremental order? It is n log n, then n squared, then n cube, then 2 power. This is the order. So now tell me which is the best algorithm. Which is best?
Med sort.
Merge sort or quick
Yes, ma'am.
sort, right? Because
Yes.
both have n log n. So n log n value is less than n only. So say n is equal to 10 means n squared is 100. Okay. But log n, log 10 to the base 2 will be lesser than 10. Okay, so always n log n is better than compared to n squared. So n cube 2 power n. So this you have to remember or you have to learn. Otherwise, it's going to be difficult. Okay, I will come back to the computations, but just an understanding for you. Okay, now let's start with bubble sort. So bubble sort, you are going to compare two elements. First two, you will compare. If it is lesser, you swap it. So if you want it in ascending order, you compare for lesser. If you want it in descending order, you compare for greater than. Okay. So two elements you will compare 1 and 2, then 2 and 3, 3 and 4, 4 and 5. Like that, two elements you will swap their positions. If it is not in order, if it is in order, you will just skip and go to the next two elements. That is what you will do in the bubble sort. Okay. Consecutive adjacent pair of elements are compared. If the element at the lower index is greater, you will swap it. And the process will continue until you reach the end. And you will repeat this procedure because elements bubble to the top of the list. One pass, you call it. That is one pass throughout the entire array. You will see that the last element goes into its position. So the next pass you will do only for n minus 1 elements. Okay. So that is why you call it as a bubble because it goes back to the elements. I will show the animation. So first what you will do, say 5, 1, 4, 2, 8 is there. You will compare 5 and 1. Since 1 is smaller, you will swap 1 and 5. Okay. Now you will compare 5 and 4. Since 4 is smaller, you will swap 4 and 5. Then you will compare 5 and 2. Since 2 is smaller, you will swap 2 and 5. Then you will compare 5 and 8. Since 8 is bigger, it's not smaller, it will remain in its place. So the first iteration till the end of the array is completed. And what do you observe after the first iteration? That the largest element in the array will come to its position. Now you will repeat this, but you will not go till n. You will stop at n minus 1 because you already know that the last element has come to its position. So you will compare 1 and 4, no change. You will compare 4 and 2, so you will swap 2. Then you will compare 4 and 5. It is no change, you will swap. So in the second pass, two elements have come to its position. So the third pass will only take into consideration these elements. So 1 and 2, no change. 2 and 4, no change. So 4 is also in position. Okay, so this is how you do a bubble sort algorithm. In pass 1, A0 and A1 are compared. Then A1 is compared with A2. So A2 is compared with A3. So that you repeat until the last position. So pass 1 always does n minus 1 comparison because it has to do all these comparisons. Right? How many comparisons are there? 1, 2, 3, 4. Right? So 5 elements is there means in pass 1, it will always be n minus 1 comparison. In pass 2, you don't compare the last element. You stop with n minus 3. N minus 2 is n minus 2 itself. So one element you don't compare. So 1, 2, 3 comparisons. So it is always n minus 2 comparisons you will have in pass 2. And the second biggest element will be placed in the last position in this. Similarly, it will keep on reducing every pass. So in the next pass, third pass, you will do comparison only till n minus 3. So it will involve only n minus 3 comparison. So in this example, if you see, 1 comparison, 2 comparisons, n minus 3. N is 5, right? So n minus 3, 2 comparisons are only done. Okay, so that's how every time the number of comparisons will reduce. But how many passes will be there? How many passes do you think will be there? Every time, how many elements get settled? In every pass, how many elements get sorted? One element, right? So to
Yes.
sort all the elements, how many passes should be there?
N minus 1.
N minus 1. So what will be the time complexity now? So n minus 1 times you have to repeat. Okay, so if it's 5, you are doing it 4 times. Correct? And each time n minus 1 comparisons. One time it will be n minus 2. One time it will be n minus 3. Right? So you can see each time this total number of passes will be n minus 1. Right? In the last pass, you will have only one comparison and all the elements will be arranged in order. Okay. Now let's look at an animation and then I will come to this one algorithm. So I have selected bubble sort. We will create an array. So I will create a random array. Okay, say 10 elements are there. Okay, 0 index starts from 0, 1, 2, 3. Okay, let's observe how it does. So let's start the sorting. So first 7, 0, you can see 2 elements are compared. If it is bigger, it is swapped. So at the end of first pass, what happens? 49, which is the largest element, comes to its position. Okay. So if you look at the algorithm, it starts from the first position to until n minus 1. That is initial case n minus 1, but last sorted element. If the left element is greater, then it swaps. If it is not, it just increments the value of this counter. Okay. So now in the first pass is over. So how many comparisons would have happened in the first pass? 1, 2, 3, n minus 1 comparisons, right? So 9 comparisons would have happened. Now this is the second pass. Second pass will run only till 8th position. So how many comparisons will happen here? Let's see. Eight comparisons have happened. Now in the third pass, you can see 7 comparisons happen. This is the fourth pass. So you can see how the pass stops with the largest element being sorted, right? So this is what is a bubble sort. There will be n-1 comparisons. Sorry, there will be n-1 passes. And every time it will compare before till the element which has not been sorted. Okay. I will show you the algorithm and we will discuss the time complexity required to solve it. Now, if you look at the algorithm, bubble sort, it takes in an input array. It starts with all the elements of the array. Okay, so first iterative loop is I is equal to, this is for the pass. Okay, and this is for the elements. So I repeat steps. I is equal to 0, j is equal to 0. If a of j is greater than a of j plus 1, you do the swapping, right? And you do this for every time j will be incremented by 1 only. So j plus 1, j plus 1. That's how you keep on doing the comparison one time. You close inner loop, right? Now you come back, repeat this for the next pass. Okay. Now there is one problem with this algorithm. Can you tell me? What is the mistake in this algorithm? Look carefully and tell me. What will happen in the second pass? How long will the value run? Actually, how long should it run? Say n is equal to 5. Okay. So in the second pass, the j should run from 0 to which index?
Oh, oh,
So there
fourth
will be
index.
0, 1, 2, 3, 4. This will be the number of indexes, right? After first pass, what will happen? The element in the fourth position will come to the right place, right? The largest element will come here. So the second pass should run till where? Only till the third position. 0 to 3 only it should run. No. What is the point in running till 4? Because already it is sorted. Even if you compare, it is going to be the largest element. So should you not reduce the number of comparisons? But what is happening here? It is always taking n-1. Do you get the problem? If two elements are always taking compared and the last element we know it's already in position. So why do you have to always go back to the last till the last position, right? Of course, this will work Answer you will get right. But what is the problem in this? It is not efficient enough because you are trying to compare elements which are already sorted. You are not taking into consideration the advantage of bubble sort, which ensures that after the first sorting, the entire element, the last element will come to its place. Right? So that is the problem with this method. So how can you solve this? So how long should the second loop run? Instead of n minus 1, what should be the value of second one? Any guesses? Do you get the point what I'm saying, why it is wrong?
Yes,
I hope
ma'am.
that part is clear, right? Okay.
Yes.
Okay. So how do you indicate that it need not run for the last position, but it has to run for only before the last position? Okay. So it is n minus I minus 1. Okay. So I indicates how many passes have completed. So initially I will be 0 when we start with. Okay. So no element has been completed. So it will run till n minus 1. Okay. Next time, one position has already been sorted. So I also will indicate it is the second pass. So when I'm in the second pass means what it does, already one element has already come to its position. So n minus I minus 1. So I will become 2 after some in the third pass. I will become 4. So the n value will also, if it is less than, if the j value is less, only it will run only if for that n minus I minus 1 value. Okay. So this should not run for all elements of the list every time. Only this will. So this position, this value should be n minus I minus or whatever is the index here, right? Minus 1. If this is k, then it will be n minus k minus 1. Okay. So n minus k minus 1 is for ignoring comparison of elements which have already been compared and gone to its position. So the last element will be ignored every time. Okay. Now, what is the time complexity? You have the complete code here. Okay. So we get the number of elements. We are just printing the elements. Then we are starting I is equal to 0 to n minus n. Then j is equal to 0 to n minus I minus 1. You compare j and j plus 1. You do the swapping, right, and repeat it, right? So what is the time complexity? Can you give me the f of n function of this? I'll give you time, 2 minutes. Try to calculate f of n function. This. You want this algorithm to calculate or this program? This is easier to calculate, right? Instead of the program, right? So please tell me what is the f of n for each of these steps. Yes, what is the time complexity? Roughly, what should be the time complexity? What will be f of n? So how many times this step will run?
n times.
N times. Okay. What about this? This step n minus, say I minus 1. Okay. What is this step? It is like just comparison, right? So maybe let's put it like 2 or 3. And
Yes.
this is 2 or 3. Okay, let's make it 2. Right? So if you add or this is repeated, right?
Two.
Okay, so it is 2 into n
Two.
minus I minus, say like 4. This is 4. Okay, 2 plus 2, 4 to n minus I minus 1. Then again into n because each pass it is n, right? So roughly you will have something like 4n squared plus some constant. So order will be n squared. Time complexity will be in terms of n squared because you have 2 iterations. Okay, though the second time the number of iteration keeps running, this one, first time it will run only for say 5 times, second time it will run for 4, third time it will run for 3. That is how it will run. But still we will always take the maximum time complexity, right? So that is why we are taking n. So the worst case time complexity is order of n. So order of n squared in both worst and average because the entire array needs to be iterated for every element to be sorted. Okay. So this is bubble sort. Let me go back to the visualization. I want you to observe this. So let's sort. Sorry, I will just create a new elements. I'll create, say, some lesser elements. Okay, let's do. Okay, now sort. Slowly observe 4325. So 50 is there. Right? So now you can see it is simple. You are able to understand. Let me increase this to say some 8 elements. And sort it. Okay, now observe. First pass is over. We are going to the second pass. So now you look, these two paths just compared and it is coming out. Okay. Now let me create a sorted array. Okay, this is already sorted array. Okay, now what do you think will happen if I do a sort of this? Why do you think in first place itself it stopped? Only one iteration ran. What does it indicate? It compared every two element and it stopped after that. Why? Just make some guesses based on whatever is your understanding. You want me to run it again? You can see.
Ma'am, it stopped at if condition, ma'am.
Which if condition?
It able to iterate the through the whole array, but in if condition in left and right, it is not greater than, so it is not able to go through the if, so it is directly skipping the if condition to swap.
No. See, first pass what happens? It goes through the entire array once. The largest elements come to its position. Correct?
Yes.
When you do the second pass, it should run second pass. No. But it is not running the second pass at all here. I will show you one example. Say I'm creating this. Okay. Same algorithm only. Now observe how it is sorting. First pass is over. Now it is doing the second pass. Second time it is going through, no?
Yes.
But it has stopped. It didn't do n minus 1 passes. If you observe, it didn't do n minus 1 passes. It stopped after the second pass. Now I'm creating a sorted array. This one. Okay. Now see, observe the sort. What happens? So based on what it is stopping the number of passes. The answer is there in the algorithm as well as what you are seeing, but you have to look at it carefully. Try. I told you it has to go through n minus 1 passes every time. So every time one element will become sorted. Correct? But you can see that this algorithm is not running n minus 1 times for every element to be sorted. After some time, it is stopping on its own based on what it is stopping. Watch carefully and tell me. The algorithm is also there. The answer is available on the screen itself.
Ma'am, here they use it right, do while swap is
Okay.
false.
So based on what they are deciding whether the pass should continue or not. There we used for. That's right. So we by default do n minus 1 passes, right? But
Yes.
here we are doing on swap. So why? Based on what they are deciding that we should do in the next pass or not. When is swap changing? When is while loop changing?
Okay. Uh,
What is the value of swapped?
false.
False. When does it become true?
When it goes to the if.
Whenever there is a swap happening, it
Yes.
becomes true. So
Yes.
if there is no swap happening at all, that is if all the elements are in order, what will happen?
There
No
is there
swap.
is no swap. Yes.
No swap will take place at all. So swap will remain false.
False.
So if there is no swap happening in one pass, in one iteration, it indicates that the algorithm has already, it indicates that all the elements are already sorted. Correct?
Yes. Yes.
So that is why you don't have to do by default n minus 1 swaps. This is still improvising the algorithm. If no swap has occurred in a particular iteration, the array requires no more processing to be sorted. It can come out of the loop. Bubble sort compares each pair of array element and sees whether it is lesser than. So when the whole array is completely sorted, the bubble sort, no swap happens in one iteration indicates that the entire array is swapped. Sorry, sorted. Okay. So now with this understanding, I will give you one, say I will create some new array. Okay. Observe this. Okay. So first iteration is over. 44 has come to its place. Second iteration is going on. So you can see every time there is a swap happening, the swapped value and the counter increments. Third iteration is going on. So in this iteration also there are some swaps. So it repeats. Okay. Now in this iteration, you see there is no swap. So when there is an iteration with no swap, it just stops after that. List is sorted. There is no need to do a comparison of 2, 5 and 5, 16. After you know that in the previous iteration, there is no swap happened, which means they are already in place. Why do you have to repeat n minus 1 times? Okay. Okay, now I will give you one more example. I will say sorted in a non-increasing order. Okay, then we will sort. Second pass is over. Third pass is over. Fourth pass is over. Fifth. Now in this, you can see n minus 1 passes are there. So the worst case of sorting, the worst case or maximum time will be taken when the array is reversed, right? We want an increasing order, but we started with a decreasing order array, already sorted array. That is when the worst case complexity will occur. Okay. Now I will take a nearly sorted array in a non-decreasing order. This, if you look, almost it is sorted, but very few changes are there. Okay, let's do the sorting. So you can see in some time, I think almost there are 9 elements, but in 4 iterations itself, the element has been sorted. The entire elements has been sorted. Okay, so that is the algorithm. So if you take note of number of swaps which are happening inside, if you add a small swap variable to the algorithm, you can just reduce the number of cycles in the bubble sort and save a lot of time in the time complexity. Okay. So now going back to the complexity algorithm, 2 loops are implemented. So first n-1 comparison, then n-2, n-3, that's how it keeps on repeating. Okay. So the number of comparisons is n-1 plus n-2. The total is equal to almost n into n-1 comparisons. So that is why the complexity is order of n squared. Okay. Any doubts in this bubble sort? Is it clear? What are the improvisations? Why the time complexity? Bubble sort is one of the basic, simplest sorting algorithm. Okay. Okay, let's take a quick break now. Come back, 10 minutes break. We will come back quickly and do the other sorting methods. Okay, let's continue. So next we are going to look at selection sort. Okay, so bubble sort is one method. Selection sort is another method for sorting. So this is also in place comparison based algorithm. So if you look at bubble sort also, we didn't go for any additional memory. We within the n elements only, we swapped those elements and compared those elements and swapped the elements. Here also we will do the same thing, but we will do the comparison in a different way. So here the selection sort, the list will be divided into two parts, the sorted part and the unsorted part. So initially the sorted part will be empty and slowly we will increase one by one the sorted part and the unsorted part will become empty. So what will happen in this process is the smallest element from the unsorted array is first selected and placed in the leftmost place, the first position. And then that element becomes the first element in the sorted path. So next we will pick the next sorted element and one by one we will place it. Okay. So I will go directly to the visualization and then come back to this explanation. So it is much more easier for you to understand. Okay, I will do a selection sort first. So we are creating, let's take random numbers. Okay, then sort. Okay, so first 14, everything is compared. Find the minimum number in the entire array. So every time, so 10 is the minimum number. So what happens when you find the minimum number? Okay, you can see that pink color that will always point to the minimum number. So how do you find a minimum number? You select the first number as the minimum number and then do a comparison. If you find any minimum number than the number you have, you rewrite the minimum number. So 14 is the minimum number, then 13 becomes the minimum number, then 10 becomes the minimum number. So once you identify the minimum number, you swap the minimum number and the first position number. So at the end of this, the smallest element comes to the first position of the array. So now this 0, A of 0 is the sorted part of the array and all the others are unsorted part of the array. Okay. Now again we'll find the minimum element in the entire array and swap the minimum element and the second position. So again now this will happen. So now minimum element 33 will be swapped. Now again the minimum element 33 will be swapped. Now the minimum element 35 will be swapped. Okay, so this is what happens in selection sort. Okay, now I will show you with another example. Okay, so now see how this happens. Okay, so now going to the algorithm. So now what is happening here? Every time the selection sort selects the smallest value in the array, right? And places it in the first position. Then find the second smallest value in the array and places in the second position. So in the first pass, you find the position of the smallest value, then you swap the first position and A of position. So this is sorted. Now in the second pass, you leave A of 0, you start from A of 1 and you find the smallest element and then you swap A of 1 and the position. So now A of 0 and A of 1 is sorted. So you repeat this till n minus 1 position. So if you look at this array, in first pass, you compare and you find the smallest element. So 9 is the smallest element. So you swap 9 and 39. So in the first pass, this becomes sorted. Now for the remaining array, you find the smallest element. For the remaining array, the smallest element is 18. So you swap 39 and 18. So 18 becomes the second position, 39 goes to the last position. Now only this part of the array you have to find the smallest. So you find the smallest one, 27, 27 and 81 will be swapped. So 27 becomes. So this part of the array becomes sorted array and this part of the array becomes unsorted array. So every step you can see the sorted part of the array is expanding. The unsorted part of the array is decreasing. So if you look at the first pass, this is the sorted part of the array and the remaining are all unsorted. But in the second, this too is sorted. In the third, this too is sorted. In the fourth, you can see this 4 are sorted. Right? Now in the fifth, you can see till this it is sorted. Now 81, 72, 90, it will find the smallest element. Swap that with the 81. So 72, 81, 90. Again, this is sorted. So once this is sorted, it will compare 81 and 90. So every time the sorted part of the array keeps increasing and this unsorted part keeps decreasing. So if you go to the algorithm, what happens? First, you initialize the smallest part, right? This is for finding the smallest element in an array. And then, so the first element is set as the smallest element. You maintain the position of that, right? And you compare all the k plus 1 elements up to n minus 1 with the smallest element. If you find any element which is smallest, right, you mark that position. So this will give you the smallest element. The position will hold the smallest element. So now you will swap position and k. So this smallest is a function which will take the entire array, the first element in the unsorted array, the total number of elements, and the position where it has to be sorted. Now, if you do the comparison, you will find in position, you will have the smallest element and k will be the first element in the unsorted array. So you will swap k and the smallest element every time. How many times you will repeat this? N minus 1 times. Okay, so this is the algorithm for selection sort. So you have a selection sort algorithm which calls a function. So this again in turn calls the position. So the position is returned. So you swap the position and the k element. Then you at the end of that you can see it is sorted. Okay. So one example we have. So sorted sublist is 0. Unsorted is all the elements. You find the minimum element 11. So this goes into the sorted sublist. That is the first position. Now again in this unsorted sublist, you find the minimum element 12. It goes to the sorted sublist and this becomes small. Okay, because we are doing in place sorting, we are replacing with the first element. Okay, now this is again 22 is the smallest. You replace 22, right? So the sorted sublist keeps increasing, unsorted sublist keeps decreasing. So in this, you start with A of 0 to 4, then 1 to 4, 2 to 4, 3 to 4. That's how you reduce the size of the array which you are searching. So the selection sort has a best case time complexity of order of n squared because it has to run n minus 1 times to find minimum element in every unsorted part. So the average is also order of n squared. Okay. Now I will go to the visualization. Any questions in selection sort? Is it clear?
Ma'am, how we will assign the lowest value?
We will search through the elements, find the lowest value. I will tell you 1 minute. Say we create an array. Okay. So first time we will take 15 as the minimum element. First element as the minimum element. Okay. And we compare every element with 15. If there is an element which is less than 15, we will mark that element as the minimum element. Okay, so if you look at the sort, you go step. So 15 red color is coming now, that is the minimum element. So until it encounters a minimum element, it will remain, 15 will remain. So now 1 is marked as the 15 element. So once we find the minimum element in the entire array, then the first element and the minimum element is swapped.
Okay, understood.
So if you look at this algorithm, it is repeated n minus 1 times, sets the first sorted element as the minimum element, and for each of the entire array, that is unsorted array, if the current element is lesser than the current minimum, that element is set as the new minimum. So this is repeated for the entire array. If this if loop is repeated for the entire array, then only the swap the minimum element with the first sorted position. Okay, this step, swap minimum with first unsorted position, happens only after the entire array is compared. So if you see this step also, so 6 is the minimum element. Okay, but if you see, it will be compared with every element. Then only 6 remains the minimum, so it is done. So now 44, 37 is compared with every element. Then once you find the minimum element, it is swapped. Okay. So now we will see an example where we create a sorted array. So what will happen if you do a sorted array? Okay, the array is already sorted. And let's do a sorting. Now first position will always be minimum. Correct? So swapping second position will always be minimum. It's just do comparison, no swapping. Third will always be minimum, no swapping. Now in this, always minimum, no swapping, right? But it didn't have any optimization. So if you look, it has, irrespective of whether the element is sorted or not, this has to keep repeating. You don't have an mechanism where you can find that the element is already sorted. But in bubble sort, what happened? In bubble sort, I'm going to bubble sort. I'm creating a non-decreasing array already. Then I'd give a sort, what happens? If the list is sorted, it does only one time. It stops. But can this happen in this selection sort? If the array is already sorted? No. It has to repeat. Completely, it has to do repeating. So there is no method of optimization even if there is a sorted array. So that is why the best case is also order of n squared. The average case is also order of n squared. The worst case is also order of n squared. But in best case can be better in a bubble sort. Right? So let me stop this and I will give a reverse array. Okay. Now what do you think will happen? Same steps are only happening. There is no much difference. Even if you give a complete inverted array or a completely sorted array, the time complexity, the number of times the loops are running is going to remain the same. But in bubble sort, what happened? When you give a sorted array, it stopped in one step because there were no swapping. But when you gave an insorted array, what happened? It kept on repeating. Right? So that is the difference between selection sort and bubble sort. So in selection sort, worst case, average case, best case time complexity is order of n squared. Whereas in bubble sort, the best case can improve because when there is no swap, it will automatically stop the number of iterations. Got it? Now, if I give a nearly sorted array also, average case, right? Then also you can see the number of times will not change much. Understood? So going back to the PPT. So best case is also order of n squared. Worst case is also order of n squared. Each step we are required to find the minimum element from the entire array and swap it. So we have to go through the entire array every time. Whereas in case of a bubble sort, right? If you look at this thing, best case can stop in one iteration itself. Average case and worst case only can go up to n squared. But in this selection sort, all the three will be n squared only. You get the point difference? Now we'll go to another sorting method called the insertion sort. In insertion sort, what we will do is, this is also in place sorting only. Here a sublist is maintained, which is always sorted. So the lower part of the array will remain always to be sorted, like the selection sort. But how do you do it is, you will pick an element which has to be inserted into the sorted sublist, and you will add it in the appropriate place. In selection sort, what you did, you always picked the element which is the minimum of all the elements and placed it in the right position, right? So there you spent a lot of time in selection sort, you spent a lot of time in finding out the minimum element. But in insertion sort, what you are going to do, you're not going to search for the minimum element. You're going to pick an element and you are going to insert it in the right place. Okay. Now you remember if you have played deck of cards, how many of you play cards, right? Say you pick card, you arrange it in your hand, right? You pick a card, you see it is a card which is like 2 or 3. You place it in the right position. You arrange it in a ascending order or whatever. So you decide, you insert it in the right position, right? So always analogy, playing cards is an analogy which is given to insertion sort because you pick it and put it in the right position. You don't pick a smallest element like selection sort or you don't compare every time. You whatever element you are selecting that you insert it in the right position. So that is why it has the name of insertion sort. The array is searched sequentially and unsorted items are moved and inserted into the sorted sublist. And this algorithm is has a problem with large data sets because the time complexity is very high, order of n squared, but best time complexity is very easy. Let me look at the algorithm and then we will. So what we do, say this is the array we want to sort. So we take 39 and we say that is the right position. So 39 is in right position. Now we take 9 and we say this is our sorted array. So 9 will come where? What is the right position for 9? Before 39. So we put it here before 39. Okay. Now we pick 45 and see which is the right position for 45 and we put it in that position. Then we take 63 and see which is the right position for 63. It is after 45. So we put it here. Then we pick 18 and see which is the right position for 18. It is less than 63, so move in front. It is less than 45, so still move in front. It is less than 39, still move in front, but it is greater than 19, so don't move, put it here. So put it between 9 and 13. So 18 is placed between 9 and 39. Now you take 81, which is the best place for 81. So it is greater than 63. So put it here itself in the last position. Now you take 108. It is also greater than 81. So put it in that place. Now you take 54. You compare with 108. It is lesser. You compare with 81. It is lesser. You compare with 63. It is lesser. You compare with 45. It is greater. So you put it here bit after 45. Now you take 72. You compare with 108, it is lesser. You compare with 81, it is lesser. You compare with 63, it is greater. So you put it here. So now you take 36. You compare with 108, 81, 72, 53, 63, 54, 45, 39, and 18. So you stop at this and you put it here. So that is what you do in insertion sort. So the main idea is insert an element into a sorted list into the appropriate position. You don't select an element, you just insert any element you get into the right position. So many people, when they play cards, this is the method they use. They start with an empty left hand, take one card, place it, take the second card, place it before or after the card. So every time you take a card, you place it in the correct position. So to find the correct position of the card, we have to compare it with each of the cards already in hand from right to left. So that is what we will do in insertion sort. So first we have an empty sorted list. We have an full unsorted list. We pick one element from the unsorted list, position it in the right position. Then take the second element, swap through the entire, scan through the entire sorted list and decide that element and then position it. Okay, so you repeat, this is your temporary position array, that is the first position is in place. You take an element, see which is the right position. So you compare all the elements to the left of that element. If it is greater, you swap it. If it is lesser, you just proceed with it. Okay, you go to the previous element. Okay, so this is how it is done. So first position element is already there. 2 you compare with 5. It is great. It is lesser. So you swap that element. So this is the step you replace. So temp is arranged to j plus 1. Now 4 you take, you compare with 5. Okay, it is bigger. So go one more position. J is equal to j minus 1. And then in this position, you insert the element. Let's see the animation. Okay, let's see it. So first 3 is taken. 29. 5 is taken. Best position for 5 is decided. 28 is taken. Best position for 28 is decided, inserted. 21 is taken. So it compares all the elements to left of it and it puts in the right position. Okay. So let me run this again. Okay. So now 45 will be in the right position. Now we will take 32 and insert it in the right position. Okay. So extract the element X from the last index to the previous index. Check if the current element is greater than the element. If it is greater, you move to the right. If the current element is greater than the element you are going to insert, you keep moving. Otherwise, you stop at that position and insert there. Okay. So see carefully. 32 is taken out, inserted before 45. 49 is taken out. So you can see 2 moves all the elements. So 11, you can see how many shift it has to make, right? All the elements has to be moved out and then only you can insert 11. Right now, what is the problem you identify from this algorithm? So when you want to insert a new element and you are putting an array, right? So what will insertion sort do? If you want to insert temp into this j plus 1 position, all the elements have to be shifted one position, right? So this will take a lot of shifting which is happening, right? So all A of j is copied to A of j plus 1. So every time there is a shifting, you have to see how many shifting is happening, which is also a time consuming. So that is why this insertion sort is not considered to be suitable for larger number of arrays. So for example, if you take this particular example, say let's say I have 22, 40, let's say 14, then I have 52, and then I have say 3. Okay. Now 22 is in position. 14 will be compared. So this will be the key initially, right? So 22 is in position. Now j will be I minus 1. Okay. So I starts from 2. Okay. So this is 0, 1, 2, 3. Okay. I starts from 2. So A of I is equal to the key. Okay. Now, if 14 has to be inserted, I compare j is equal to I minus 1. So this 0, j will be 0. Okay. If j is greater than 0, we will only do this loop. So 22 will not be changed. Okay. Now, when you take 14, right? 14 is greater than the key value, which is taken as the 22. Sorry, 14 is the key value. This is greater than 22. So you shift j to j of 1. So A of 0, that is this 22, is shifted to next position, j equal to j minus 1. All the elements are shifted one position. So in this case, it is only one element, and j plus 1, the key value, is added. Okay. So this way you keep shifting all the elements in the insertion sort. So this is a considerable headache, or it is you keep repeating shifting elements. When the list is already sorted, it gives you the best case because you don't have to keep on shifting elements. But the maximum time, the complexity, if you have an inverted array, then the number of swap will be very high, and it will go to a worst case complexity of n squared. Okay. So let me show you this. Let's create a sorted array. Okay, list is already sorted in this case. I will share the visualization. So if it's already sorted, you can see it is very simple. It compares only with one element. It gives you the best case. And only one time it will run and it will stop. So best case, if the list is already sorted, it works very well. But in case we have an inverted list, okay. See how much time this algorithm is taking. So every time entire list has to be swapped one position. So you can see 47, 45, 44, 43. Every time they have been swapped one position. So you can see what will be the worst case time complexity when you have to keep when you give a really inverted array, every time it has to shift. And if you take a nearly sorted array, right, it will take an average case, but still the number of options will be better. Number of comparison will be better. So you can see after this, it is just checking with only one element and it is able to finish fast. Okay, so I will stop here for today. So now my question is how clear is it on the sorting? 3 sortings we saw: selection sort, insertion sort, and bubble sort. I hope you understood how the time complexity is decided: worst case, best case, and average case. And I hope you understood how it is necessary that we take, if you think that you will always have a worst case sorting, then you will not, you can better go for something like insertion sort or bubble sort, because if you think that you will have many best case options, right, then you can go for insertion bubble sort, because selection sort will not give you any advantage if you even have a best option or not, right? So that is where you this sorting which one is best will be decided. Okay, so I will stop here. I will open the forum for questions. One more reminder, quiz is open. Please submit the quizzes without any delay. There will not Okay, go through the recordings. If you have any questions, please let me know. Go through the digital content. If you have, go through the labs for practice. If you have any doubts, please let me know. Thank you all.